Ever wondered if warp drives could create gravitational waves? First off, let's talk about warp drives. Popularized by shows like Star Trek, these futuristic engines have a surprising basis in real physics. Back in 1994, Mexican physicist Miguel Alcubierre proposed a concept that could, theoretically, let us travel faster than light. Here's how it works. A warp drive wouldn't actually propel a ship faster than light. Instead, it would create a warp bubble around the spacecraft. This bubble would contract space-time in front of the ship and expand it behind, essentially moving the universe around the ship. Sounds crazy, right? But there's a catch. To make a warp drive work, it needs something called negative energy density, which doesn't exist naturally. Scientists have come up with theoretical workarounds, but for now, practical implementation remains out of reach. Now onto gravitational waves. These are ripples in space-time caused by massive objects accelerating like merging black holes. Recently, some scientists have been pondering whether a failing warp drive could emit these waves. Imagine a warp bubble collapsing. Would it send out detectable gravitational signals? If a warp drive distorts space-time like merging black holes do, it might just produce gravitational waves. But here's the twist. A stable, constant warp drive wouldn't emit any waves and has no ADM mass, which measures energy content. So are we close to creating warp drives and detecting their gravitational waves? Not quite yet, but the possibilities are tantalizing, and who knows what the future holds. The EM drive, or electromagnetic drive, is a concept for a spacecraft thruster, first proposed by British inventor Roger Scheuer in 2001. Unlike conventional rocket engines that expel propellant to generate thrust, the EM drive operates by reflecting microwaves inside a cone-shaped metal cavity. This idea is particularly intriguing because it seems to generate thrust without expelling any propellant, which, if true, would violate the fundamental law of conservation of momentum. NASA's Eagle Works laboratory has been at the forefront of testing the EM drive since its proposal. The device supposedly generates thrust by bouncing microwaves inside a closed cone-shaped cavity. However, the scientific community remains skeptical due to theoretical inconsistencies and measurement errors. Recent independent tests in Germany suggest that the thrust observed is likely due to electromagnetic interactions rather than the EM drive itself. Earth's magnetic field interacting with power cables in the chamber appears to be the leading explanation for the small thrusts seen during testing. So what makes the EM drive so controversial? Let's delve into the theoretical challenges. First, the principle of conservation of momentum. The EM drive claims to generate thrust without expelling any propellant, contradicting this fundamental principle. In classical physics, if an object gains momentum in one direction, something else must lose an equal amount in the opposite direction. Second, Newton's third law. For every action, there is an equal and opposite reaction. If the EM drive produces thrust without propellant ejection, it challenges this law. Critics argue that the observed thrust might be due to experimental errors or electromagnetic interactions rather than true propulsion. Third, the lack of a robust theoretical foundation. The EM drive's proposed mechanism involves microwaves bouncing within a closed cavity, but the underlying physics remains unclear. Without a solid foundation, it's challenging to explain how the device generates thrust. Finally, energy conservation. The EM drive's apparent thrust suggests energy conversion from microwaves to kinetic energy. However, this process isn't well understood. If the EM drive violates energy conservation, it would disrupt our understanding of physics. Despite these challenges, the EM drive remains a subject of ongoing experiments and debates. Independent researchers in Germany built their own EM drive to verify its performance. Despite controlling for various factors, they couldn't fully shield the device from Earth's magnetic field. The tentative conclusion is that the measured effect results from this magnetic interaction, not the EM drive's propulsion mechanism. So is the EM drive a breakthrough or a bust? The jury is still out. While it offers a tantalizing glimpse into a new realm of propulsion, the scientific community demands rigorous proof and a solid theoretical basis before embracing such a revolutionary concept. Now let's turn our attention to the broader quest for faster-than-light, or FTL, travel. How close are we to achieving this sci-fi marvel? Theoretical concepts. The idea of FTL travel isn't just confined to the realm of fiction. Theoretical constructs like warp drives, wormholes, and the Alcubierre drive suggest manipulating spacetime itself to create shortcuts or paths that exceed the speed of light. However, these ideas hinge on exotic matter with negative energy density, a concept that remains purely theoretical for now, with no practical implementation in sight. General relativity and limitations. Our understanding of gravity and spacetime is governed by Einstein's theory of general relativity. In this framework, massive objects warp spacetime, affecting the motion of nearby objects. To achieve FTL travel, we would need to bend spacetime in entirely new ways. The Alcubierre warp drive, for example, proposes creating a warp bubble around a spacecraft, but it faces significant challenges related to energy requirements and stability. Energy requirements. Warping space-time isn't easy, it demands immense energy. The energy density required to create a warp bubble far exceeds anything we can currently generate. While exotic matter with negative energy density might offer a potential workaround, its existence remains speculative and unproven. Quantum mechanics and uncertainty. Quantum mechanics adds another layer of complexity. The Heisenberg uncertainty principle introduces limitations that affect our ability to manipulate spacetime with precision. This uncertainty further complicates the already daunting challenge of achieving FTL travel. Current progress. So where do we stand today? The short answer is that we are still far from realizing practical FTL travel. Our current focus lies in understanding the fundamental physics that govern our universe, exploring quantum gravity, and studying extreme cosmic phenomena like black holes and neutron stars. Hope for breakthroughs. While we can't predict when FTL travel will become feasible, the history of science is full of unexpected breakthroughs. New discoveries could revolutionize our understanding of space-time and propulsion, bringing us closer to the dream of faster-than-light travel. We've journeyed through the realms of warp drives and the tantalizing quest for faster-than-light travel.